Hello, I'm Bruce.
Hi, I'm Aditya.
We are the Risky Scientists. I teach risk management at the University of San Diego.
And I teach data science at Harvard.
And this is our main episode for the week. This is very exciting for me because I get to learn about machine learning from you, Aditya. This is a term that we're hearing a little, increasingly so, in the discourse about COVID-19. And I'm eager to hear what it is. So please tell us.
Well, Bruce, I think that's the million-dollar question. Everybody talks about machine learning, and I think it's so used in such a variety of contexts that people basically have no idea what it is. And I think machine learning is being used to refer to a variety of different things that correspond to basically computers learning something about the world, most generally. But I think a better way of thinking about machine learning is to think about a continuum or a set of classes starting from linear regression, which we can talk about in a moment, all the way up to general artificial intelligence. So let's talk about regression for a moment. So linear regression is basically just the process of having a set of points in space. We've all done this. You have a bunch of dots and you want to draw a trend line. And you say, well, why do we want to draw a trend line? Well, the reason you would want to draw a trend line is because we may want to make some prediction about the future. So, for example, with COVID cases, we may say, look, there's been 100 COVID cases last week, 200 this week, 300 next week. What's going to be the number of COVID cases in 4 weeks? And that sounds like the sort of basic math problem that one might get, right? So you draw a graph and you say, oh, look, in 4 weeks, here's where the graph lies. So I think in that, hopefully we're unearthing one of the purposes of machine learning. One thing that I always find very perplexing is people talk about it without understanding, well, why are you using it? And I hope we can come back to that. So one thing in my mind is, why are you using machine learning? And one purpose is to make predictions about the future from the history of the past. It's basically using computers, which can process very large amounts of data compared to humans, which we are very good at intuition, but limited in the amount of data that we can process. So that's linear regression. And I would argue that much of what happens in machine learning is actually closer to the end of linear regression than the other end. So let's talk about the other end. On the other end, we have general artificial intelligence. So, well, what is general artificial intelligence? I think general artificial intelligence is basically a computer that is completely self-reliant. So it's an artificial intelligence that is capable of learning independently, that is capable of making judgments independently, that basically doesn't require the human at all. And we certainly haven't gotten there yet, if we will ever get there in the future. So that, I think, is not something that when we talk about machine learning, we should be at all thinking about right now, given our current state of the world.
Yeah, so I guess for me, a problem arises here if we're conflating linear regression with machine learning, because linear regression, as you correctly describe it, this is something you can do with pen and paper.
Yep.
And presumably the machine learning version of linear regression is just, you're using software to draw that line or to compute the slope of the line. You're using software to do the mathematics of it. So for me, if all you need to do to get to machine learning is to use software to do something you can do by hand, that doesn't sound very exotic, right? And yet the term is used exotically, a bit like big data and modeling, particularly computer modeling. It lends an air of exoticism. And also, as we've discussed on modeling, it lends an air of irrefutable science. So if you are modeling, if you've got big data and you've got machine learning, who are we to argue with you? Because we don't understand what you're doing, and because you're using computers, you must be doing something special. So I become a little, what's the right word? I become a little nervous if machine learning is used so broadly,
right,
and it's loaded with this added value that there's something special, as something exceptional about it. But in reality, it may just be a software program that draws lines for us.
Right, absolutely. And I don't want people to get the wrong impression. There are certainly advances, and most of the current, even your standard machine learning libraries that I think maybe 80 or 90% of people in the data science world are probably using. They're using these variety of languages. Python is very popular now. So if you're using Python as a software program to basically draw trend lines for you using some sort of machine learning algorithm, the mathematics behind that is more complicated than the mathematics behind drawing a single linear regression. That is true. But at the same time, it's not more complicated in the sense of being completely crazy, and it's not like the computer is coming up with all of this stuff on its own. There's still a basic underlying framework. Much of machine learning is still using the basic matrix algebra that we use to solve basic systems of equations. The scale is much bigger. And in a sense, I think much of the rewards that we're seeing now for machine learning can be attributed simply to scale. That's not always true. There are certainly some very clever things that people can do that's not just a factor of scale. But a lot of it is, I mean, if you go and buy a car from let's say, a large automaker like Toyota, they're certainly getting discounts because they're buying in volume. Or if you go to Costco. And so you're able to get that data, and you're going to able to get a lot of it and leverage that. And that's, in a sense, what's happening. So let's talk about, for example, object recognition. So this is in the news now. So if you want to recognize, say, a wolf versus a dog. Now you say, well, how is that the same thing as recognizing as a trend line? It seems completely different. Well, let's think about what a wolf is really, right? So what is a wolf? A picture of a wolf is a two-dimensional picture. It's a matrix. And so I can take a picture of a wolf and basically turn it into a matrix with numbers. And let's not get too technical, but usually those numbers go between 0 and 256, which tells you basically how intense something is, right? So a very bright spot might be a 256. Black would be 0. So I take this image, I convert it into a set of numbers, and now I have a set of numbers that has a label. And so we're getting into something that a set of numbers is associated with a label, and that's really no different than saying that somebody is 6 feet tall, and what you want to do is you want to build a laser device to separate people who are above 6 feet tall versus less than 6 feet tall. The complexity, of course, arises in what we call features. So when we talk about features, it's what are you looking for that separates these two categories? And that's where machine learning is really powerful, because this computer can look at a very large number of features all at once incredibly quickly. Whereas for a human being, if you wanted to try and, so let's say you're a veterinarian, and I know nothing about this, so I'm just hypothesizing here, but suppose you decide to make a measurement of the snout length of a wolf and the snout length of a husky, and then the toe size, and then the ear size. And it would take you a very long time to do this. But for a computer, it's able to do this very, very quickly and learn, and that's where the learning comes in. It learns which features are most important. And if you're able to figure out which features are most important, now you have a distinct advantage. And now you're starting to talk about things that can be beneficial. But really, coming back to it, it's the same thing as saying, look, here's a trend. There's things above my line. There's things below my line. It's just that that line, if we want to think about it in space, becomes much more complicated.
So can I ask about this learning part then?
Yeah.
So it sounds like the term is literal, that we're talking about where the machine is learning, right? So the machine itself is learning. So that it's clear that artificial intelligence belongs under that term.
Yeah.
But why would a linear regression belong under that term? Because you can program the software to do the mathematics to calculate the slope of the line, but is the machine really learning anything?
Very good. So I think it's worth talking about two types of machine learning at this point. One is supervised machine learning, and the other is unsupervised machine learning. So let's talk about supervised machine learning for a moment, which again I think is probably what most machine learning is right now, at least in terms of the development of the field. And why? So you say, well, why is drawing a line? Why are you learning anything? well, what are the compromises? We've talked about trade-offs before. We have to ask, what are the compromises you have to make when drawing a line? Unless your points are perfect, and in the real world, you never get perfect data. So if your points are perfect, it's easy. You just draw a line and you connect all the dots and it's a perfect line. But normally you can't connect all the dots. So you have to figure out, well, do I bias slightly up or do I bias slightly low? Do I want to connect these dots or do I want to connect these dots? Do I want something that minimizes the error, the variance, or do I want something that gets most of the points spot on and say the other things are crap? And that's the learning part, right? So if you're a doctor and you want to figure out, if a patient comes in, you want to figure out, well, which of these symptoms are relevant and which ones are not. That's the same process. You want to figure out which points to prioritize, which symptoms to pay most attention to, and which ones you can ignore. And that's the learning process.
Okay, so is it then fair to say that machine learning always involves some form of artificial intelligence, at least in the sense that the machine is adapting or improving its algorithms or its procedures? Is that fair?
I think in most cases that is true. I would be worried, though, to say that that is artificial intelligence, because I can write a basic machine learning script from scratch using just code, and it doesn't seem to me that there's really much intelligence in it. It's executing a program, and often if you just go out and you'll see, if you run a machine learning algorithm, you'll see them as called epochs, right? So cycles of learning. And you'll see, but I can code in cycles of learning, right? I can say, well, test this, this, in this case, and then find the best one. And then test this, and this, and then find the best one. So it's in a sense, sequential optimization is learning. But whether you call that intelligence, I don't know. That's maybe up to...
No, so should we even call that learning, right? So sequential optimization could include something like narrowing your error terms, or improving the decimal placing, so improving your accuracy, the mathematical accuracy. Yeah. Is that really learning? So is optimization really learning? It's just optimization, isn't it?
Well, that's a tough question, I think, and maybe that's not for me to decide. I think there's cases in which you would call it learning. For example, if you're learning how to play the drums, you're offbeat, and you get closer and closer and closer, right? So that's a process of optimization. Are you learning how to play the drums, or are you just practicing? I don't know. It certainly doesn't feel like you're necessarily discovering something new about the world in the sense of learning it in that sense. But I guess it's learning in the sense of learning how to do a task and do it well.
If we're optimizing accuracy, that doesn't seem like learning. If we're optimizing our performance of a task, that does seem like learning.
Right. Well, that's a good point. So I think maybe the learning here comes from the inferences that you draw from the optimization, right? So it's from these features. So if over the process of, if you get really, really good at separating huskies from wolves, have you really learned anything? I don't know. But in the process of getting really good at separating huskies from wolves as a veterinarian, if you've learned something about bone structure, if you've discovered something about the differences in bone structure, the differences in size, if you've discovered some sort of generalizable principle, then perhaps that counts as learning. But just the process of saying this is a wolf and this is a husky is not learning, perhaps.
Okay, so how do we get through supervised or enter unsupervised machine learning and then to artificial intelligence?
Yes, so I'm certainly not a full-time computer scientist. I know people are working on all kinds of different algorithms. Basically, what you want to try and do at a high level is you want to teach the computer to code itself. And if you remember, we talked about features and principles. So if you can give a computer principles by which it can revise its own programming, then you're starting to get into the realm of general AI. Unsupervised machine learning is actually maybe, while it is quite a thing, it's maybe not even the same as general artificial intelligence, and it's maybe not as impressive necessarily as it sounds in most cases. There might certainly be very impressive cases of unsupervised machine learning, but in most cases, what you're doing when you're giving a machine learning network something and saying it's unsupervised, what you're saying is that you're asking the computer to find the features for you. So instead of saying, look, I want to separate, I'm going to keep coming back to this example because there's some other point I want to make about it later on. I want to separate wolves from huskies. So instead of saying, I am going to ask the computer, instead of a human being, I'm going to say to the computer, look at these characteristics. So look at the nose size, look at the paw size, and look at this. And then based on that, I'm going to tell you which one is which, right? So you're giving the computer a very clear set of characteristics. Unsupervised says, look, go and figure out what's different between these two things. And so you try a whole bunch of combinations, and we won't get into the mathematics of how you do that, but basically you try a whole bunch of different combinations, and then you say, look, these differences are the most substantial, in my opinion. And because these differences are the most substantial, those are the things that we should be using to try and separate the two tasks. Supervised machine learning, on the other hand, almost always requires right now, a human or a label that is generated in some other form. So in supervised machine learning, you're still in the place where you need some external factor to tell you whether the machine did well or didn't do well. So you need a supervisor, so to speak. Well, I think there's also a perversity in people getting caught up. We were talking about accuracy. So there's a perversity in this accuracy game that people are playing, though, with supervised machine learning, which I think is probably really not constituting learning. So I'm very glad you brought that up. And the perversity was saying, for example, I think there was a network recently that said that it could distinguish wolves from huskies at 99.9% accuracy, or some absurdly high level of accuracy. And then you say, well, okay, how do you do this? And you say, well, look, I gave it a bunch of pictures of wolves and I gave it a bunch of pictures of huskies. And the machine learning system is perfect, basically perfect. Well, the problem is I don't think a veterinarian could distinguish the two at that level of accuracy, right? I mean, there's crossbreeds, there's all these things that I don't know enough biology to say, but it's certainly not something that a human who's making the original classification can do perfectly. So how are you saying that a computer that is trained based on these metrics is able to do it perfectly? And so you go in and you look at how they actually did the study, and it turns out that the way the computer was able to distinguish wolves from huskies is not because it really understood anything about wolves or huskies, but because all the pictures of wolves had snowy backgrounds. And all the pictures of huskies had, huskies frolicking in people's backyards or inside their houses. So it's able to distinguish these two things at incredibly high levels of accuracy without having learned anything about the true nature of what a wolf is or what a husky is. So I think that's the real danger in this, and especially the danger in looking for features is, yes, the computer found a feature. The feature was, is there snow? Or the feature was, is it a pet? The feature was not something about anatomy or something about the actual biology of wolves or huskies.
I mean, I think there's a lesson there that we've spoken about before in the context of controlled experiments, is that this was a bad experiment. They did not control for the background.
Right. Yeah, absolutely. So I don't want to sound like I'm saying machine learning is all terrible, but it's very powerful when used appropriately.
Yeah, but it sounds like it's also very easy to spin.
Yeah.
Or you know what I mean? It's easy to exaggerate the power of your tool, like as we've discussed with big data and computer modeling. It's very easy to pull the wool over your audience's eyes and say, we've got this exotic thing and it's producing this incredible level of accuracy, but don't you worry about how we actually did it.
Right.
And there's an incentive there not to allow too much transparency, which is a problem we've seen in COVID-19 modeling, because then that transparency would lead to exposure of the dirty tricks that people use to fudge programming errors and bad assumptions that are leading to unreliable results.
Right. I think that's very well said. And that isn't to say that there is, that we know everything about how computers are so successful at this. So I think we have a pretty good understanding of how the current kind of some of the best machine learning networks, these are usually something that's called a neural network. And again, that's another term I hate. The field is so full of these terms that make very little sense. So it's not a neural net because it's behaving exactly like our brains. Because as soon as somebody hears neural network, they think, oh my gosh, what have you done? You've taken a whole bunch of human brains, hooked them up together, and now you have a super brain. No, it's not that at all. It's a mathematical technique called backpropagation, which is a very complicated technique, no doubt about it. And the way that these neural nets work is that we kind of understand how to do backpropagation. Otherwise, we wouldn't be able to build these systems. What we don't understand as well is just why backpropagation is so successful. So a priori, you've developed a matrix, you've developed a solver, you've developed a system. There's no reason to assume that the system should be as good as it is. And that is really, in my mind, the amazing thing about machine learning is that not that we don't know how it works, not that it's a complete black box, but that it works so much better than we would predict just mathematically, that there's maybe some new mathematics to be discovered, or there's some principle going on here that we don't quite understand just yet.
So that sort of frightens me as the non-mathematician here.
Yeah.
If you say that we don't understand how well it's working, then, I mean, there's two ways to spin that. You could say, isn't mathematics great?
Yeah.
Or aren't computer networks great that they can do things beyond our expectations? But you can spin it the other way and say, well, if you don't understand fully how it's working, isn't there space, room for errors,
mm-hmm.
and an over-reliance on something you don't understand, which could lead you, maybe in a minority of cases, to significant errors, say in modeling pandemics, that you cannot spot. You can't spot these errors because you don't fully understand how the network is operating.
Yeah, I think that's certainly a concern, that we shouldn't be using these systems to make predictions about where we think the world will be. Perfectly. I think that, especially when making predictions, there's something we really should be talking about here, which is overfitting. And overfitting is the process by which you say that you have a perfect system because it connects all the points, but actually then what you're doing is you're just responding to noise. And I think it's a really interesting question of how do you make a robust machine learning network? People are working on this. And they're working on how do you try and filter out the noise and filter out, basically make sure the system doesn't respond to every little thing, and because it doesn't really know what's more important or less important, right? It's just trying to look for everything, hence the power, but also the danger. But in the meantime, I think there's probably two things that I would keep in mind. Item number one is that we want to be aware that the true test of theory, and we talked about theories briefly earlier, is in prediction. And item number two is that we need to be thinking about what a machine learning network usually tells you. And what a machine learning network usually tells you is it gives you a probability, not certainty.
Right, Aditya, so it seems to me that machine learning would be more useful in certain disciplines, like particularly physics, than, say, some of the social sciences, so or even some of the applied sciences. So how is machine learning used in physics?
Yeah, it's interesting you say that, because I personally have actually found it quite surprising to see how quickly machine learning has pervaded physics. I mean, I think even several years ago, it was mostly let's use it to identify pictures, or I mean, I think it's very clear how you might want to use it in terms of trying to come up with ways of playing online games or warfare or things like that, where and we can talk about, that's a whole different type of network, actually. It's very clever. But in physics, it's actually come up quite often now, particularly in And I don't know how far I would go with this. So there's one very clear use of machine learning in physics, and I'll give you an example, is the Ligo experiment. So you might have heard of the very long experiment that people did to try and discover gravitational waves. And it won the Nobel Prize in Physics a few years ago. And one of the big questions when you're trying to understand or discover gravitational waves is that it's an incredibly sensitive measurement. So you say, well, how do you make this incredibly sensitive measurement over distances of potentially thousands of miles? Because we're trying to measure the compression of the Earth over thousands of miles potentially. And you say, well, what happens if an elephant was walking above my detector? I mean, that would make much bigger difference than the gravitational wave. And so I think it's been very cleverly used in places like this where people train a machine learning network to detect noise. So you detect what a car rumbling across the freeway 5 miles away sounds like. You detect what a miniature earthquake sounds like. And the differences it makes in your measurements. And you train a machine learning network with a ton of data to detect these things very accurately. So now when you're trying to make your actual measurement, it's very easy to say, well, not easy, but relatively much easier to say, look, this is not a real measurement, or this is noise on top of my actual measurement, and I should subtract this away because it's something else. And so I think that gets at the general principle of what machine learning systems might be very good for, which is pattern recognition. Another area that I think is potentially promising in the medical field, for example, that a radiologist might miss a spot. But if you have a machine learning system to scan and look for these slight abnormalities, they're very good at looking for things that look odd, things that look not quite right. I mean, looking at snow, right? I mean, so they're very good at looking at these random things that seem a little bit weird. So I think that's where I've seen it as very promising in places like physics and medicine. The place that concerns me a little bit more, I saw an experiment recently that said that because they ran a machine learning system and it produced a result that was consistent with a theorem in physics called the Equipartition Theorem. Basically, it's a theorem about the energy of molecules. So they ran one of these big simulations and they said, look, the system eventually converged on a rule, so it was optimal when it obeyed the physics laws, and therefore the machine learning system had discovered this principle of physics. I don't quite buy that yet as a derivation of a physics principle, because just because you've come to something as an optimal doesn't necessarily mean you've discovered it as a real principle. So that's where I'd be a little bit more skeptical, I think, for a little bit longer about whether machine learning is really offering something. But certainly in terms of pattern recognition, pattern detection, looking through large data sets and finding the anomalies, I think it's fantastic.
Right, so can this pattern recognition be useful in the response to COVID-19?
Right, so I think the answer generally is yes. I think generally we've seen some evidence of people actually using these large computer systems. Exactly what form of machine learning, exactly what algorithms people are using, I actually don't know. But certainly you can look for patterns, for example, with vaccines or tests, where what you want is something that will either simulate the spike protein in the case of COVID, right? I think that's what many people are going for now. Or you want a structure that will bind to the spike protein and therefore make it useless. So if machine learning systems can be used, for example, to try and come up with patterns, again, thinking about patterns is the big thing here, I think, to start recognizing the patterns of things that work and the things that don't work in simulation. So you run simulations of these different molecules and you say, well, does this simulation work and does this simulation work? And if you can start to understand what separates the ones that work from the ones that don't, that's where I think it can be very helpful, especially if you can start to get at the principles behind that separation.
Mm-hmm. And I could imagine it'd be useful too for recognizing patterns of behavior, human behavior, in response to COVID-19. So how do people socialize? How do they change their economic activities?
Yeah.
How do the people who get infected, how do they get infected?
Yes.
There's a pattern to that. So is it true to say that it would be useful there? And if it would be useful there, should we be seeing more machine learning in response to COVID?
Absolutely. I mean, it seems like we should be, but we should also be cautious because based on what you talked about with patterns, right? So you can also use machine learning systems to make diagnoses. So based on your symptoms and other information about your travel history, it would be very plausible, I think, to come up with a machine learning system to say, look, let's compare the travel history of 200 million people. Let's compare the some other symptoms of 200 million people. And the machine learning systems, this is what they live and breathe, would probably come up with a rule to separate the people. And your training data would be, look, these people got COVID, confirmed positive by a swab test or whatever you want to use, and these people didn't. What's the difference? And the machine learning system will come up with a rule, and it'll tell you the difference between this group and this group, and it will predict, given somebody's travel history and symptoms, whether or not they have COVID. Well, you say, well, what's the danger? Well, this is, I think, something that also very much disturbs me in how machine learning is being used. And it's that people think that the judgment that a machine makes is a real judgment. And it's a perfect judgment, and it's a binary judgment. So either it is or it isn't. And in fact, if you go and look at the algorithms, most machine learning systems use something called a softmax. So you say, what on earth is a softmax? Well, when you give a machine learning system a choice, so does somebody have COVID or not, given some set of history? So there's only two choices there, yes and no. And almost all machine learning systems will not tell you yes or no. They will tell you there's a 62% chance that they have COVID and a 38% chance that they don't. And then what do? Well, we like certainty as humans. So most of the time what we do is on top of that result from the machine learning system, we put in something called a softmax layer, which basically says, take the value of highest probability and state that as the result. And so this is what you see in all these systems. So when a machine learning system says something is a wolf, it doesn't say it's a wolf. It says, of all of these dog breeds, maybe the wolf is the highest probability. And then we come in and we say, no, look, we want to get rid of that uncertainty because we like certain results, and we're going to make it print out an actual result, which is fine in some cases. For example, self-driving cars, you need to decide whether it's a stop sign or not. So you have to make that judgment. But in other cases, it feels like the probabilistic judgment is the more useful one. So I'm very much for using these tools to help us, but I don't want us to forget that these tools are probabilistic. They are stochastic. And if we forget that and start relying on these systems to give us certainty, it becomes, I think, very dangerous.
Yeah, I suppose it reminds me of our discussion about evidence.
Yeah.
Where we had to warn that a lot of evidence is judgmental. In popular discourse, evidence is often treated like proof, which means you either prove something is true or it is false, and it's treated as a binary condition. But actually, often your evidence is probabilistic. So probably this happened, and now we're making a judgment about whether that level of probability is sufficient for us to judge that it is true or not. So it seems like we've got a similar problem here with machine learning. How then can the ordinary member of the public, the lay person, how can they judge then the quality of research or policies or prescriptions that are based on machine learning?
That is a very good question, and I think the tools to judge research that is based on machine learning is very much the same set of tools, thinking tools, that we have been talking about so far. I think the danger comes in when we think of machine learning as a miracle pill or as a perfect system because it's somehow going outside of human judgment. But in fact, I think the things to ask with a machine learning system, thinking about what the training data is. So I don't think most systems are general AI. So most systems learn from some set of information that a human so far has put in front of the computer, however that's fed in. So we should be curious about what that training data is. Are there any correlations in that data, like having snow in the background, that makes the the data put in actually useless. In machine learning systems, it is mostly true that quantity helps. But again, quantity will help you with accuracy, not with whether your measurement is actually valid. So again, we need to go back and ask, well, what is the quality of the stuff that we're putting in? Quantity might help you go from 92% to a 99% accuracy rate, but what does that even mean? Comparing machine learning judgments to what we know in terms of theories is the other thing. So we talked about theories. So thinking about trying to be a little bit theoretical, I think, is actually a good thing in the machine learning world, because you're not so caught up in data and saying, I'm going to feed, pump data into this machine without thinking about what I'm actually trying to do. So it's all the same stuff, in my opinion, just a little bit more, and in fact, I think I would be even a little bit more careful with machine learning, just because it's incredibly powerful, which is exciting, but it's also, I think, relatively new. And I hate to make this claim, but I think it's true that most people who use it don't quite understand it. And even the people who are at the forefront of it, and that's not a necessarily a completely damaging claim, it's just that we're still trying to understand it. So it's useful, but whenever I use a machine learning system, I think it's certainly with the knowledge that it's remarkable, but it's something there are so many unknowns, and we have to be careful about that.
So Aditya, this has been fascinating, and I'm so grateful that we're able to address a term like machine learning, right, explain it and interrogate it, where in the normal discourse it's a term that will be thrown around and used casually as if we all should know what it means and you shouldn't think further about it. So this is really useful, so thank you.
No, thank you. I think we certainly haven't explored all the depths, and it's just it's a beginning. But to put it in machine learning terms, I'm very thankful for this GAN, and I'll leave our listeners with that. GAN is GANN, and it stands for Generative Adversarial Neural Network. And the way that a GAN works is exactly like what we're doing. So you have one machine learning system trying to trick the other machine learning system. And so by this process, they actually both become very smarter. So you might say, feed me, now you're seeing this with fake images of celebrities, right? So one system is tasked with the job of determining whether somebody is a celebrity or not, and the other system is tasked with the job of generating a fake image to trick the first system. And I think hopefully by having these sorts of dialogues and interrogating these questions, we're doing the equivalent, and we'll learn.
Yeah. Thank you, Aditya. This has been a fascinating episode. So thank you all for listening. We are the Risky Scientists. Bye-bye.
Thank you. Bye-bye.